truly thank you very much for inviting me for this wonderful workshop. It is a great opportunity and also for me good memories because the first time I was here was in 1981, invited by Jean-Paul Poirier, who was quite present in the first lectures. And already then I was working on salt, so you can imagine. So I used to be a creeper like you, but now I'm not so much, and it's been quite a long time since I've done a real deformation experiment. But I was at one point forced to actually use these creep data of myself to make models, which was very confrontational and painful. So I hope that maybe you can learn something from that. Certainly there are a lot of people who contributed to this work, PhD students, postdocs, Chris Byers, with whom I've done most of the early work on salt. So I would like to acknowledge them all, and you are going to see the names coming on the slides showing who have done which part of the work. What I'm going to do is I'm going to first give you a little bit of an appetite of why it is really cool to work with salt. And then I will go through the classic work on dislocation creep, then on grain boundaries, the effect of fluid, pressure solution creep, and then on the interaction of these processes in rock salt. And in the end, I will try to give you some natural examples and also some really amateuristic modeling so that Boris can shoot at me in the question time. So why is salt cool? Well, you can go into it, and I think that all of you would really love to go into the mantle and look at pictures like this. You have amazing possibilities to sample the material. This is a salt mine that we are working on in the Carpathians. And you also already see that there are obvious signs of deformation at all kinds of scales. If you zoom out nowadays, you can take Google and watch salt domes. This is in the Kavir Desert in Iran, where a 3.5 kilometer salt dome with different lithologies actually comes to the surface, piercing the rocks, and you can see the beautiful structures showing that there is a lot of ductile deformation. And this was kind of the state for a long time until about 10 years ago, when Shell offered us to use for research purposes 10,000 square kilometers of high resolution 3D seismic. And we started looking at the Zechstein in the north of the Netherlands. So here is the gas field where all the earthquakes are happening. And we discovered that there was in the Zechstein salt, which is pink in this picture, a very good reflector. And this is a 30-meter thick anhydrite layer. It's called stringer. And this can be mapped in a regional sense. And if you map it, then you can visualize the surface of this 30-meter thick anhydrite. You see below it the broken basement, and then this anhydrite layer is folded. So this is this profile here, but at the same time it's ruptured. So the anhydrite, first of all, has a very complicated rheology, but also it shows us how the salt is deforming. So suddenly 3D seismic has given us amazing insight in the internal workings of salt. This is our seismic survey. It's about 10,000 square kilometers. This is the Groningen field, the huge gas field in the Rood-Ligand. On top of this, there is the top salt. And you see that the top salt is completely different because salt is very weak. And of course, that is something that we all know. And it decouples the tectonic deformation of the basement from the overlying surface. But now if I show you the regional picture of the stringer, of this internal layer, then you see this. And this is probably the most amazing picture that came out of our lab in the last 10 years. You see that the salt flow has ruptured and deformed this stringer in completely different ways. In this area there is not a lot of deformation, and there are these ruptures here, and here the deformation is very, very strong. Another reason why I work with salt, because you get jobs. In fact, the drillers who are drilling many holes through this salt, they don't like to drill into this anhydrite because it's overpressured and it gives you all kind of drilling problems. So every well that the oil companies are trying to drill goes through the holes in these boudin necks. So understanding boudinage at this kind of scale in salt is really giving you a very important practical application. All right, so the salt is deforming, and we can really get a kind of a multi-scale understanding of what salt is actually doing. But what is the rheology of salt? Well, so let's go back to the really classic works. This is 1972, the work of you heard. And what he has produced a lot of stress strain curves at 2 kilobar pressure, so there was a lot of confining pressure on the salt, and he has seen that there is a kind of a power law relationship at a lower strain rate between differential stress and the strain rate. Another very large part of the work was done by Neville Carter and his co-workers who have deformed Avery Island salt to quite high strains at 10 to the minus 9 strain rate. So just imagine how long this experiment has taken. And they have also found that there is a kind of a climb-controlled creep. The exact mechanism wasn't so clear. And this salt, the Avery Island salt, which is a very nice homogeneous kind of salt, has a water content of 0.01 weight percent. But there is water in it, and they have already recorded it. You can measure this water content using infrared techniques. And please keep this in mind, because it will come back as a very, very important thing. They also tried to look at the microstructure, and this work was inspired by the early work in the solid-state physics group, who have discovered that you can make very nice edge pits in sodium chloride and all those ionic crystals. I think Amelinx is the main name to name there. And of course, for all the geologists, you know that rock salt, if you make a thin section, you don't see anything because it's isotropic. And if you cross your polarizers, it's black. So what they did is they broke the samples, and they've taken small crystals out of it. It was quite an amazing kind of work. And then they etched these crystals, and they have demonstrated that there were lots and lots of dislocations, subgrain walls, all the beautiful networks which were formed there. And this was important because they have basically laid the basis of a subgrain size piezometry. They have shown that there is a very, very nice relationship between the differential stress and the subgrain size, and this was then applied to natural rock salt. And in this picture here, this is the natural salt. They have derived from the subgrain size that the differential stresses are very low. Of course, we have known that, but now it's quantified. And after this, there has been a lot of additional work. So now there are hundreds of these measurements in all kinds of different settings. And we know that in very, very gently deformed bedded salt, the differential stress is rarely above 1 megapascal. In domal salt, it's mostly between half and 2 megapascals. And this is something which, of course, is a great way to test numerical models, because if your numerical models where you calculate the tectonic motions produce 25 megapascal differential stress in the salt, then your model is wrong. There are some very interesting examples where the differential stress can be high in salt terms. I mean, we have seen much higher stresses, of course, but up to 5 megapascals in the cold stems of diapirs that really come to the surface, and in some alpine trusts where these salt deposits were interpreted to have undergone earthquakes. So just imagine. The dislocation density was also measured using this edge pit techniques, and so this is a famous paper from 1983 by Carter and Hansen. And the dislocation density also scales very nicely with differential stress as expected. All this work from the American laboratories was, I think, inspired by the need to create a waste disposal site for nuclear waste. And of course, this has been a controversial but also very actively researched and discussed topic, the rheology of salt in the VIP site. So the point I'm trying to make here is that this was fantastic work, and they really tried to do the microstructures, but they didn't really have the tool to look at the grain boundaries. There was just no observational technique to do that. And when I started my PhD and we started working with Chris Spires, we also took the domal salt. This is now from Germany because that's a bit closer. And here are a set of stress strain curves, very, very similar to everything that has been measured before at 150 degrees, and I think 10 to the minus 5 strain rate, but at two different confining pressures. At confining pressure, which was quite low, I think just a few megapascals, the rock salt dilates a little bit, the volume change goes up, and at high confining pressure the rock salt compacts. And then after these experiments we did stress relaxation tests, and what you saw is that the samples which dilated, these samples here, had this kind of log strain rate, log differential stress relationship, but the samples which did not dilate became much weaker at very low strain rates at the end of these relaxation tests. And this was, of course, this was unexpected. This was completely contrary to anything that has been found before, but nobody has done these kind of stress relaxation tests in salt. And also, this domal salt has a very, very small amount of water in it, 0.01%. But what we found is that there is a very easy and simple technique to actually look at the microstructure of a rock salt. What you do is you polish the samples, and then you etch the surface with a slightly undersaturated sodium chloride solution, which basically dissolves the surface. And then the big trick is to clean these surfaces, and we got from crystallography a technique to use a hexane, which is a completely non-polar fluid, to wipe the solution off the surface. They are using this to image crystal growth spirals, for example. And that technique suddenly opened up microstructure of salt, and what we have seen is that all the samples that we have studied that did not dilate were recrystallized. There was a subgrain structure with a subgrain size exactly as expected, and there were lots and lots of big new grains without any dislocations. And the point is, and we have done quite a lot of observations, and we have shown that these grain boundaries contain a fluid film, which is a saturated solution, and it is just 45-50 nanometer thick. But this fluid film increases the mobility of these salt grain boundaries by many, many orders of magnitude, and allows the salt to recrystallize almost at room temperature. So that inspired us to do another set of experiments where we made artificial fine-grained rock salt, so really small grain sizes, and then make them wet with a small amount of brine, and then the steady state strain rate of these salt samples was much faster at the same stress as ever found before in sodium chloride work. So we found a major weakening. during long-term creep under these conditions. The samples that dilated didn't show this. And that we have explained that because the samples who dilated couldn't form these grain boundaries because they dilated and the water could evaporate. So we started looking at dislocation creep with water-assisted dynamic recrystallization at the grain boundaries as a very important process. And this was taken up in the laboratory of Chris Spires, and there was quite a lot of important studies there. This is the paper by Jan ter Hege about his PhD, where he has done wet salt experiments at 75 to 250 degrees C, lots and lots of experiments with different strain rate and different flow stress, and he found this dislocation creep power law relationship, and the wet samples were quite a lot softer than the dry samples. So these two samples here are dry samples, and look, this one is 125 degrees C dry and 75 degree wet is about the same strength profile, and this one is 175 degrees and the same strength is 100 degrees wet. There is and there is a critical amount of about 4650 ppm water, and that is enough to weaken the salt. So the point or the problem in these early studies was to actually create dry salt. It is not very easy to make salt dry. All salt in nature contains a small amount of these fluids, and the way that you can make dry salt is to melt the salt, solidify it, and then keep it completely dry. You know, never open the window, and then make your samples artificially, and then you can make dry samples. In wet salt, which is basically everywhere, and I would now predict that those Avery Island salt samples that were studied by Carter and Hurd, they all recrystallized in the same way, but they just never discovered it because they didn't have a way to look at the microstructure of the grains, and they never did these stress relaxation experiments. These grain boundaries are highly mobile because they have this very, very thin fluid film in them, and if there is a dislocation density contrast on both sides of this grain boundary, then on one side of the grain boundary, the solubility of in this brine becomes a very, very small amount higher, and that creates an ion flux across this grain boundary. And because this grain boundary is so thin, and because the diffusion in fluid is so high, these grain boundaries can migrate very, very rapidly. You know, you can make a quick calculation if you want 0.01% water, if you have a 3-4 millimeter grain size, is enough to wet these grain boundaries with this 40 nanometer film. There was a very nice paper by Colin Peach and Chris Spires and Pat Trimby, who have derived an equation describing the velocity of these grain boundaries, and this constant in the equation here depends on the rate controlling mechanism. Of course, there are different candidates. You can have dissolution as a rate controlling step, you can have diffusion across the grain boundary, or you can have the precipitation. Depending on what kind of rate controlling parameters are there, the energy here, the activation energy, represents a different process. But taking really simple values for these kind of migration, Colin calculated that the velocity of these grain boundaries should be maybe 10 millimeter per day. Yeah, so that is really, really fast in rock salt. And in fact, there is a beautiful experiment that any of you can do very easily. You just take a spoonful of table salt, you put it into one of your beautiful presses and press it really quickly to make it completely solid. And then you make a thin section and you can watch it recrystallize in the microscope. It happens that quickly. Um, so this grain boundary fluid film was of course elusive for a long time because it's not so easy to see 40 nanometer thick fluid films. Um, we studied using magnesium chloride salts in a miniature triaxial cell where we could actually watch these grain boundaries, and here this is a grain boundary, and you can see these fluid inclusions which are connected to the grain boundary that is migrating. Here's the grain boundary changes. There's another one. There is another one here. And if this works, then I have a movie now. There you go. So you see this grain boundary, and here are the bubbles, the fluid inclusions, which play this game with the grain boundary. They go into the grain boundary, they come out of the grain boundary. This is a beautiful movie made by Oliver Schenk during his PhD. Here's a grain boundary dropping the fluid and leaving it behind. And the beautiful thing is that, in fact, from simple optics, you would expect this to be completely black. But the reason why they are not completely black is because of a quantum tunneling effect of light coming through these really, really thin fluid films. Later, we got a new toy, which is the cryogenic ion beam electron microscope, and there we could freeze these grain boundaries with a fluid film and then polish them in cryogenic state with an ion beam. And these are actual images of these different fluid-filled grain boundaries made by Guillaume Dubois. And he wrote a very nice paper about all the different kinds. And you can also see that in some positions these grain boundaries kind of start to break up, which will come back later. Another beautiful example, and I put in quite a lot of examples of this grain boundary fluid film because not many people were convinced in the beginning that these films actually existed. This is a study by Cesar de Meer and Chris Spires, who made these fluid films in a sodium chloride crystal pressed against a glass plate. So what you are seeing here, this triangular shape, is an actual fluid film of sodium chloride with a glass plate under stress. And then he made FTIR Fourier transform infrared measurements of these grain boundaries, and he has shown that there was between 50 and 200 nanometer thick fluid films on these grain boundaries. So I think that by now it is really convincing that these fluid films exist, and they make the grain boundary velocity in the rock salt very, very high indeed. As a conclusion, we looked at quite a lot of these salts from all over the world, and when you look at domal salt from the Zechstein, then you can show that there was extensive dynamic recrystallization, and this was formed by slow natural deformation. Dislocation creep is of course the process that is giving you the deformation, and grain boundaries are moving all over the place, wiping out the energy in the crystals. So here in this picture you see grains which have lots of subgrains. Here is another picture of that, and here is a new grain which is growing and eating the subgrains. This picture, this blue picture, was really given to us by a kind of a completely unexpected discovery that if you color rock salt blue in a certain way using high energy gamma rays, then it first turns brown, and that is quite well known. And if you do this irradiation to a very high doses at about 100 degrees, then it turns blue. And the blue color is because the chlorine atoms are knocked out of their position into a double chlorine defect by the gamma rays. And then at high temperatures of 100 degrees, these defects are starting to migrate, and they coalesce into small colloidal sodium defects or sodium impurities. And the size of these colloidal sodium is enough to give you the blue color. And the whole trick about this is that if you irradiate the salt to very high doses, then everything is totally blue. But the nucleation of these of these impurities, if these little colloidal sodium particles, is very, very strongly dependent on the defect structure of the salt, impurity atoms, dislocations, subgrains. And this is, if you do it just right, then you have a fantastic method to decorate all the substructure in the sodium chloride. So the German Science Foundation gave us this irradiation facility, which is in the Munich nuclear reactor. It's open for everybody. If you have salt samples, you can send it there. And in fact, it's very simple. The reactor is, of course, complicated, but we just have a container, this little thing here, and we put the salt samples into the container and we stick it in the spent fuel element part of the reactor. And so then you get the structure, and what I like really much really is this grain that has kind of growth bands, and also at this point it has this strange blue colors, which I think were fluid inclusions that were dragged by the migrating grain boundary, building some kind of a defect into the structure. So dislocation creep, but also dynamic recrystallization, fluid-assisted dynamic recrystallization, and in fine-grained material, which is also wet, there is this very, very strong weakening, which we interpreted to be caused by a solution precipitation creep process. So putting all this together, at about 60 degrees centigrade, you could make this line, which is the power law creep equation for dislocation creep, and at a very, very fine grain size, so this is just 100 microns, the salt is much softer, and this is really nice because it helps us to extrapolate to the very low strain rates during tectonic deformation, and also to the by using the grain size, we can also extrapolate to much coarser grains, and you can get to rates which are basically not achievable in the laboratory. So these are the two equations. This is the dislocation creep equation, quite well known, and this is the pressure solution creep equation, where there is this grain size dependence. And the grain size dependence it can be quite strong or much weaker depending on the rate controlling process in these grain boundaries. The interesting point is where these blue lines cross the red line. And this was elaborated by Hans de Bresser and Jan ter Hege, and Hans developed this field boundary model, where he has shown that if you calculate the transition between pure dislocation creep and pressure solution creep in this log stress log grain size diagram, then all the recrystallized grain size piezometers that have been established in rock salt fall exactly at this boundary. And so the hypothesis was that dynamic recrystallization establishes a grain size which makes sure that the half of the strain rate is given by pressure solution creep and half of the strain rate is given by dislocation creep. And if you change the stress, then the grain size will adjust with that. So depending on the stress, if you keep deforming your material, then the grain size is going to grow if you drop the stress. We know for diapiric salt, that the differential stress is about 0.5 to 2 megapascals. I've shown you that in the beginning. So right now we can put a diapiric flow of rock salt in this region. And this is quite important because if you want to model this, it is not so important to know what viscosity or what effective viscosity the salt has. You have to just make sure that your model deforms in this region. There is another really nice way to check this independently, and that is to look at the diapiric rise, and this is Mount Sodom in Israel, and I was really grateful for the invitation just a few weeks ago to go there. So this is a mountain of salt at the boundary of the Dead Sea, which is moving. It's coming out of the subsurface at about 7 millimeters per year. And using INSAR techniques, you can actually measure how quickly this dome is coming up, and you can invert that data. And there is this beautiful paper by Rami Weinberger and his co-workers, and they independently determined that the rock salt viscosity is about 10 to the 18th pascal second, just exactly the same as I've shown you in this orange circle. And the shape of the velocity field of this dome, which is coming out of the subsurface, is suggesting that it is a power law fluid. So it kind of fits together, and we have all kinds of independent observations pointing to this concept. So now let's look at the pressure solution part, which we have already indicated a little bit, but we haven't really discussed. There has been a very, very large amount of work in the laboratory of Chris Spires. Here's a famous picture from Peter Schutjens' thesis, where you can see sodium chloride crystals that are not deforming but truncating each other and indenting. Depending on what controls the process, there is a linear grain size dependence, or if the diffusion is the rate controlling step, then the grain size is very, very strongly influencing the strain rate. And this process is the most prominent in the glaciers of salt, of which the most beautiful ones are found in Iran. This is a picture by Salman Yahani, who did a PhD and got 40 hours of helicopter time to fly over these domes. What you see is the central mountain here. This is where the diaper is coming out of the subsurface. And what you see here is the rest, the relict of the salt glacier, which used to be much thicker and was washed away in the wet periods. So the salt is probably not flowing anymore today, because it is now a dry period. But this is, of course, the famous picture that you can all make using Google Earth. And if you ask yourself, how can the salt, with the rheology that we have determined until now, flow down the hill, then you come to the conclusion that it can only be if it's really fine-grained and deformed by pressure solution. And here we worked together with Prokop Zavada and his co-workers, who went into this salt mountain, which is really quite amazing. Everything around you is salt. We have taken lots of samples and did quite a lot of studies. Notice that now the salt forms cliffs, so it is obviously not flowing at the moment because it is dry and the grain boundaries have dried out. But if you look at the microstructure, and there are quite a lot of papers that we have published now, there are no subgrains, the grain size is very small, and what you see is dissolution precipitation creep. So the salt glacier is coming up out of the earth. Here in the cold diaper stem that I've mentioned before, the stresses are quite high, and then the top of the salt comes into the rain, and it recrystallizes into very, very fine-grained salt, and it becomes much, much softer. It's like a pile of ice cream that melts and flows on the table. Joel Schleder has done some beautiful work showing how these old grains are surrounded by recrystallized fine-grained stuff without any subgrains, without any dislocations, deforming by pressure solution creep as a kind of a salt myelinite. And EBSD work that we have done shows that there is no preferred orientation whatsoever, which is of course consistent with the absence of crystalloplastic processes. So coming back to this picture, what is happening here is that in the diaper stem, the salt is deformed at these stresses of maybe 5 MPa, and then it recrystallizes, it becomes much finer grained, and this fine grained salt is soft enough to actually flow down at a very small slope on the slopes of this mountain. Okay, so we have these fluid films at the grain boundaries. Pressure solution is also activated by these fluid films, and we have a kind of a concept of recrystallization moving along this line, adjusting the grain size. But if you cycle the stress and if you change the conditions, then the salt is going to recrystallize and become much weaker. There is one additional complication about these grain boundaries. So this is my 40 nanometer thick grain boundary here with the fluid inclusions left behind. You have seen them in the movie. That if you decrease the stress, or if you dry out the salt, then there is a thermodynamic driving force to make these fluids into small pockets because of the interfacial tension. If the fluid is non-wetting, if the wetting angle is not very small, and this actually happens. There's been a very nice model by Reinhard van Noort, who has considered that there is a kind of a critical stress for these fluid bubbles at the grain boundary to start to neck down and form isolated fluid pockets, which are then just connected by solid state grain boundary, and then of course the pressure solution creep stops. So there is a kind of a lower differential stress, and this has been shown very nicely in the experiment from Chris Pierce's lab, that the pressure solution stops. And there is you can call this as a kind of a yield stress. And if the material is relaxed and allowed to relax to a flow stress which is low enough, then pressure solution will stop. Now, if you look at grain boundaries in Zechstein rock salt, and we have looked at many, then the grain boundaries actually have this kind of re-equilibrated structure. This is the work of Mark Sadler, who built kind of a big U stage to actually tilt these grain boundaries to parallel to the optical plane, so that he could photograph them, and he made a beautiful collection of how these fluid films neck down into these sausages or isolated bubbles, and in some cases they actually form the remnant of fluid films. And if you want to see more details of this, then you can look at the broad ion beam SEM pictures of Guillaume Dubois. This time the salt has been dried, so the fluid inclusions are now empty, and you can see here is a grain boundary, and here is one of these big fluid inclusions, and apparently there was still a little bit of fluid inside the grain boundary, because after the ion beam cutting we got a small amount of efflorescence in the vacuum, showing that there was in the depth of the sample still a little bit of fluid present. So sometimes there are films like here, but in most of the time in equilibrated salt the bubbles are really isolated, and so in the Zechstein, in the salts that we have looked at, but also in these salt glaciers, the grain boundaries are not active. They are not highly mobile because of this resetting, because of this low stress re-equilibration. So if we now look at the domal salt, what happens if we drop the stress? In the Zechstein, this is what has happened, because in the tertiary there was a long period of tectonically quiet time where the differential stresses in the salts were very low, and now we can ask ourselves, if the stresses drop, does the salt relax like that and is actually quite soft, or does the salt relax like that? Just for the geologists in this group, this is the kind of typical picture of a Zechstein salt dome, and in the tertiary period, basically the whole salt domes are just kind of covered by sediment. There is very little deformation. There is a lot of possibility to relax the differential stresses, and it is 65 million years, which is a long time. And now if I go back to these anhydride stringers that I've shown you in the beginning, then in the top part of the basin, these stringers are in 3D completely isolated. So they are 300, 400, 500, 600 meter size anhydride blobs, which have a density of 2,900 kilogram per cubic centimeter, and they are surrounded by rock salt, which has a density of 2,200. So these anhydride blocks should be sinking. And basically this is a kind of a Stokes rheometer that is given to us, because these stringers now are all at the top of the salt, embedded in the rock salt, and we know that there was a very quiet period of 60 million years in which these could have sunk to the bottom. Shiyu and Lee did some finite element calculations, and he calculated the stress field, the differential stress field, around a 300 meter size fragment. And what you see, it is very, very low. It is a few kilopascal, yeah, 125 kilopascal. So really we are now interrogating this part of the deformation mechanism map. The deformation, the stresses around this stringer are very, very low, and we ask ourselves, is this stress enough to actually make them sink or not? It depends on which of these flow laws are applicable. As you will see here, that there is a 6 order of magnitude difference in strain rate, so that's very, very big. And what Shion has done is he made these stringers in the salt dome, and one of the models is the n equals 1 flow law, and the other is the n equals 5 flow law. And after the end of the salt tectonics, where he formed this kind of pillow, he let the two models stand for 60 million years. And what he has shown very nicely is n equals 1, all the stringers sink to the bottom in 60 million years. N equals 5, the stringers sink maybe 30, 40 meters. So it was not this one. Yeah, once the grain boundaries are mobile, we have the fluid films in the salt, but we drop the stress. The rock salt does not remain in this state for long enough to allow these stringers to sink to the bottom in 60 million years. And the reason is that the grain boundaries harden. And that is why all over the Zechstein we actually find these healed grain boundaries, which means that after the end of the salt tectonics, when the stress start to relax, temporarily the salt is quite weak, but then it freezes like gelatin. And it becomes a power law creep material, which under these conditions deforms basically at almost zero strain rate. There is another little example that is quite illustrative to this one. This is a bedded salt studied by George Leder, very, very gently deformed. You see some diagenetic cores of old grains surrounded by a salt which is full of subgrains, pointing to a very, very low differential stress. And there are some new grains. You can see the salt has actually started to recrystallize, but if we look at these grain boundaries, the old grains are full of fluid inclusions, the new grains have no fluid inclusions, so these grain boundaries must have been wetting themselves during migration all the time. There was a lot of source for fluid, but still not all of the material is recrystallized. And I think that this is another example of the fact that if the differential stress drops sufficiently, the grain boundaries freeze and they cannot migrate anymore. So, do I have a few more minutes? So rock salt deforms in all kinds of different places in this rock salt cycle. There is of course the bedded salt, which then comes into this diapirs, and then it flows down the hill as a salt glacier, and then here it is dissolved and deposited, and there is a waiting for the new geological cycle of deformation. And what I hope that I showed you is that the rheology of the rock salt in this cycle can quite dramatically change. For example, so the most dramatic one is that the salt comes to the surface and becomes really soft. But in the salt itself, when tectonic stops, then the rheology can change quite quickly. And that is, of course, a very interesting challenge for the modelers to implement the rheology, which is depending on strain and also on stress. And to show you an example of the kind of model, this is, oh wait, I'm going too quickly. So this is a model made by Alexander Wright using abacus with three different rheologies. This is the rock salt using the power law, and I will explain to you why we did that. Here are the anhydrite layers which have boudinaged in an early stage. These anhydrite layers are about 100 times more viscous than the rock salt, and then there are potassium magnesium salt layers here which are much weaker. And when Alex runs this model, I think I have to click one more time. Yeah, now it's running. Then you see that the salt pillow is starting to grow. And of course in the center there is quite a lot of shortening. And if we choose the rheology of the anhydrite layers just right, then we get the folds, but not too much, but also not too little folding. And because of these early boudins, you get these huge shear zones inside the salt. So rock salt is much more heterogeneous than we think. Most of the time it can have all kinds of heterogeneities. And the reason why we chose to model this with a simple power law rheology is because the stresses in this particular model are rising all the time. And if you rise the stress during deformation, then you remain on this line of the power law creep, and the grain size is kind of decreasing. If we would have slowed this model, then the stress would have dropped, and then we would have had a lot more trouble doing this. So, in summary, what I try to do is to give you a little bit of an insight on how this rheology of the rock salt during natural tectonic deformation can switch from one to the other mode of deformation. This can be a hysteresis because of the change in boundary conditions, and this is a really nice challenge for a modeler to actually build this kind of flow law into the state-of-the-art numerical modeling schemes. So just to show you one final picture, because rock salt is of course also of a lot of practical importance, and during this is the flow law of the BGR, the German state authority for geology and resources, and they don't see this change in N. Yeah, there's been a lot of experiments. They've spent a very large amount of resources measuring this without any microstructural work on the deformed samples. So the engineers who are now preparing the radioactive waste disposal site in Germany in the famous Gorleben repository are only calculating with this flow law. I'm cutting this a bit short because the opinions are now slowly changing, but there was another idea, and this was Heimin Koyi, who thought, okay, well, the viscosity of salt that is coming out of all kinds of field studies is 10 to the 18th. So let me take a Newtonian viscous 10 to the 18th material and take these anhydrite blocks in my repository, and he has shown that in 750,000 years the radioactive waste repository is going to sink 0.5 kilometer into the salt. Now I think that is a good thing, because if it gets deeper it won't come up. But the problem is that there is a real big controversy between the geologists and the geological models for what is going to happen to this waste disposal site and what the engineers who are making the predictions think. And if you ever want to convince the public that you know what is going to happen to your radioactive waste disposal site, then I think that these disagreements cannot remain. They have to be solved. I think they are quite easy to solve, but they really have to be done. So thank you very much.